So all noise will appear as input to the two-port network. So we have to compute all the noise, total power because of all the noise and average it out because the noise is going to be a mean square value, right? So you have to find the average noise power. So you have to divide by the averaging factor due to the input source. That is where you find the noise factor. So one easy method is to compute the short circuit mean square current and divide that by the total short circuit noise current due to the input source. So if you want to find the noise factor due to current, you consider the same formula. You consider the total output noise power due to the current source. Yeah, whatever current source you're going to have input divided by the total output noise due to the input source. So if you have voltage, you use voltage to compute the noise factor. So ultimately, I need the noise power, right? So noise power, I can derive it from voltage or current. The voltage means you know it is V square by R. Power current means you know it is I square into R. So whatever method we follow, whether we are going to consider the input source to be a noise voltage or input source to be a noise current, that does not make any difference because ultimately we require noise power. So the whatever method, either if you're going to use a short circuit current source or an open circuit voltage source, whatever mechanism you're going to follow, the noise power is going to be the same. So if you carry out this computation method, so when you combine all the noise sources, it is going to be very tedious because each one is varying in a different way. So I cannot bring them under the same umbrella. Okay, so that is why they say that in a two-port network, all the noise sources are uncorrelated. Uncorrelated means you cannot bring them under a common similar parameter because noise is completely random, right? So no, you can never try to form a relation between the two types of noises. So for a two-port network, the noise is going to be always uncorrelated noise, and the expression for noise figure they have derived. So it is F is equal to IS square plus IN plus YS EN the whole square divided by IS square. So this IS square is because the input source. I told numerator will have input source plus due to the device noise. So two components are there. If the device's noise is not there, then F will be equal to 1. That is what we have seen previously, or it is equivalent to 0 dB. So this is the noise factor which they are defining. So some books they relatively use noise factor and noise figure, but we strictly assume them to be different. Noise factor will relate with power. Noise figure will relate with SNR. So that is a very, very important formula. So although we have assumed that the noise is uncorrelated, so we can definitely try to use the mathematical equation and relate what is the different components of noise. So we use two components, right? En and In. En is the RMS noise voltage and In is the RMS noise current. So we can consider In to be considering two components, In equal to IC plus IU. So IC will have a correlation with En which is proportional to it. So that IC relation is given by IC equal to IC into En. So Y is going to be the admittance of the device. See, actually, it is mathematically, it is uncorrelated. But if you want to mathematically find the equation for noise factor, only when you relate them, you can find. So we assume that the noise current In and the noise voltage En are correlated, but actually they are not correlated. We are assuming it for the purpose of computing the exact formula for noise factor. So I am splitting In in terms of two equations, IC plus IU. IC will have a relation with IEN. So in this way, I have correlated IN and EN. And IU is going to be completely uncorrelated with EN. So one term is correlating, one term is uncorrelating. Result is going to be uncorrelating. So only when both are correlating, when you add, it will become again correlated. I have considered one term to be correlating with En and one term to be not correlating. So effectively, the sum is also not correlating. See, all these are probability concepts which you can understand that they are considered to be random variables. So these value of En, the value of In, IC, IU, you can never find it at, using an exact numerical formula. All these are completely random. That's why you try to find correlation. When where you apply correlation only when the parameters are scattered, and I try to relate all the parameters. Okay, so that is why I have related IC with